Okay, so good morning, everybody. We'll go ahead and get started on what will be hope a crazy sort of run in to the rest of the semester. As you know, it's week 10, so we have a normal week this week. You have spring break next week, and that'll hopefully give me an opportunity to make some adjustments here to what I'm doing, and hopefully things don't get too wonky. Um, it's going to be sort of an weird situation. You're going to see a bit of a disembodied voice. I'm recording this on an iPad so that I can then upload it to YouTube. So you're going to see pin strokes with a disembodied voice, so to speak. And so, that'll hopefully, we'll see how that goes. Um, as I said, this is, for all intents and purposes, week 10. You should treat it as a regular week, and as much as that's possible. You have lab this week. The lab instructors will have information for you with respect to that. So you should be prepared. If you haven't seen it, then at least they should be reaching out to you and talking about it. So let's talk a little bit about what we're going to be doing here. As I said, I'm recording from the iPad and be uploading this to YouTube. So a few things just sort of about the nature of what's going on here. You're used to seeing boards, so what you see on your screen will be similar to that. You're also used to having boards kind of pre-filled, either with a question and with a little bit of writing. So that's what you'll see here. Again, the hope is to try to keep this as normal as possible. And obviously there's going to be some adjustments for me trying to think about how to pace information, how to split it out. So, for example, one of the things that you'll notice is that the iPad's smaller, so you're going to see more boards per lecture because really I can't have to maybe take a concept at a time. So you're going to see more boards than what you're used to, but hopefully if I keep track of my time well, then we can do that. I think that's another thing too, that it might be a little bit of awkwardness just in terms of how timing matches up. When we're all together, of course, sometimes you're asking questions and doing things like that, and I won't have that here. So while I'm putting material together for what I think will be, an hour and 15 minutes, some days we may finish short, that time. I'm not going to guarantee it, so don't get too happy about that. But the fact is, without your sort of like feedback and kind of connection, I won't have a good sense for how information will be timed and what will be a good amount of content for a particular day. So we'll work on that and come to that together. So as I said, used to seeing all of these things, and my goal is to just try to keep things as normal as possible. As it stands right now, if you're watching this video at your normally scheduled class time, I am in the Discord chat server, so you're welcome to log in there, listen to this in real time, and then ask questions if you want to over there. And for those of you who aren't here or have other commitments, that's totally fine. You can watch the video and come to office hours to ask questions. So everything here, at least in terms of what I'm trying to do, will hopefully just be business as usual. And like I said, we'll work together and try to get it going. So just like we do every day at this time, we're ready to go. Let's row the boat. Okay, so what I wanted to do was to start with something that we ended up with. The Tuesday, Thursday folks are going to get a little bit of new information that the Monday, Wednesday folks have a little bit of review on. But we talked about factors that affected stroke volume when we were looking at intrinsic regulation of stroke volume. And so what I wanted to do was just kind of revisit that. So if you look at your Wiggers diagram here, this is the volume trace. So just to make sure we're thinking about this, this was the volume trace in the left ventricle, just to make sure we're on the same idea. So if you take that out and look at that trace, then that's what you're going to see here. So remember at the end of, right before we had ventricular ejection, so this is a little bit of review, still trying to work some review stuff in so that we know, so we're still kind of thinking about this stuff. We knew that from Dr. Allman's lecture that there's right before the ventricles actually move, right as the ventricles contract, there's a moment in time in which the ventricles are contracting, but because the aortic semilunar valves are closed and the mitral valves are closed, and we haven't generated enough pressure to push push the aortic semilunar valve open, volume doesn't change. And we called that the isovolumetric ventricular systole component. So that's what we're looking at here. And then we gave that a name. We called this end diastolic volume, or EDV. Now, the moment that the volume starts changing, and we have ventricular ejection, then we get something called ESV, or end systolic volume. Okay, so those were some terms that we were working with both in lecture before and then from the Wiggers diagram. So we're going to build on that a little bit today, and we'll just kind of remind ourselves that the difference between our EDV and our ESV is what we called stroke volume. And this was an important regulator of our cardiac output. Right? We said that stroke volume times cardiac output, stroke volume times heart rate was cardiac output. And we looked at different ways of changing that. And so we talked about some ways of modifying that. And so, for example, if we had an increase or a decrease, in heart rate, then we talked about the fact that that could lead us to have a situation where if we have more filling time, then we could say that our EDV might increase. Hold on, let's try that again. Let's say that our EDV might increase. Okay, so that was to be the case of a decrease in heart rate. We also looked at ways of affecting it where if we increase the force of contraction, right, then we could see something where rather than having an ESV that looked like this, if we contracted more strongly for the same volume, we called that contractility, then our ESV could change. And so the idea is that if we look at either changes in EDV or changes in ESV, both of those together will change our stroke volume. So for example, if we looked at a situation where we had that would be our new stroke volume. All right. So the idea then is that if we think about stroke volume is simply equal to EDV minus ESV. And therefore, anything that changes EDV or ESV can change our stroke volume. And that's an important thing to think about. I think one of the overriding factors when we start talking about the cardiac cycle and we start looking at the dynamics that go into that, having a measure in mind of, what if we decrease heart rate, for example, that can change our stroke volume. And as we talked about with respect to Frank Starling, if we decrease our heart rate, then we get a change in stroke volume, not because we changed our ESV, right? But because we increased our EDV. And so that's going to be something to think about. So I'm trying to frame the initial start of this with a review of stroke volume because now, right, I'm just going to move on to the next board here. Now, what I'm going to try to do is to catch myself and at a moment like this, not talk for 10 seconds. So you can put your YouTube video on pause, and then that'll give you an opportunity to kind of write down what you need. Okay, so hopefully that was a long enough pause, or if you need more time, obviously you can pause the video. So what we're going to look now then is we're going to ask this question of what is the relationship between pressure and volume, and in particular we're going to look at the pressure inside the left ventricle. So if we look at what's going on here, what we really are looking at, is trying to understand volume in the left ventricle, pressure in the left ventricle, and then as a function of volume in the left ventricle. Now, one lecturer has seen this already, so I'm going to sort of talk about it in broad strokes here. This is called, an appropriate term is called a pressure volume loop, or a PV loop for short. And for those who haven't seen it, this is just another way of depicting the cardiac cycle. So I've got some numbers here, 1, 2, 3, and 4, that just sort of correlate roughly to about what we expected to see in that circular figure, that circular representation of the cardiac cycle, and a little bit of what Wiggers is doing. So the thing to notice here that's special about the PV loop is kind of like my favorite way of thinking about what's going on with the heart, is that there's pressure on the y-axis and volume on the x-axis. So there is no representation of time here, and time is what we call implied. So how do you work through this? What you can do is you work through it in a counterclockwise motion. So we started 4, move around to 1, or start here, move to 1, 2, 3, 4, and then back. And so by doing that, we can simply look at different elements of the cardiac cycle and then relate them to this diagram. So I think there are a couple of things to look at here. The first is to try to identify parts in this diagram where the volume is changing, but not the pressure, and to find times where the pressure is changing, but not the volume. In other words, as you can see here, as we move from 4 to 1, the volume is changing a lot, and it's increasing. So let's make sure we put it this way. So volume is increasing in that direction. But interestingly enough, when we look at here, the pressure is increasing, but the volume is actually not changing. So that right there can kind of give you a sense of how you can relate work here to the cardiac cycle. So if we start here, we can say that because the pressure in the heart is not changing, but the volume is, this would be equivalent to our fill time, or our late diastole of the heart. All right. Remember that in the, so then, right, we would move into ventricular. So this is all ventricular pressure. So to make sure we're thinking about this all ventricle here. So now what we can think about is that when the ventricle starts to contract, there's this moment wherein the pressure builds, but the volume doesn't change, right? And we said that at that time, there's enough pressure in the left ventricle to close the bicuspid valve, but it doesn't push open the aortic semilunar valve. And so we called that isovolumetric ventricular systole. So this is isovolumetric ventricular systole. Okay, so that's what's happening between 1 and 2. Now we can also use this again to keep in mind some of the elements that were there. I'm going to sort of call your attention here to this little blip in the curve here. This corresponds to atrial depolarization. This is because and right when the atria contract, they then generate a pressure gradient that moves blood from the atria to the ventricles. And so you see this slight increase in pressure and a little bit of increase in volume. So in your Wiggers diagram, that was that little bump that occurred. Let me go back up here. That would be equivalent to this part right here. When you see that little bump, that change in volume, that's because the atria have essentially contracted. Okay. Now let's go back to this then. When we looked at how once the ventricles contracted, they pushed shut the mitral valve, right? But didn't have enough for the bicuspid valve. Just to make sure we're using the same terminology. They pushed the bicuspid valve closed, but they don't have enough pressure at this point. They can push the bicuspid valve close, but they don't have enough pressure to open the aortic semilunar valve. So we gave that a name. What was that name? That was the first heart sound, or S1. Now, the other thing that we have to understand about this point, and that's also true, is that we talked about this idea of EDV. Remember that the end diastolic volume was the volume in the ventricle before before we had ventricular ejection. So this point also represents, sorry, again, kind of moving things around here, so I'm still getting adjusted, forgive me. We also have to consider that this also represents the EDV. And we also give that another name, and I'll write that down here. We also call the EDV what we call the preload, or the amount of blood in ventricle when it contracts. Okay, so if we work our way around, again, we can see there are lots of different elements here. The only thing that we're adding new, though, is this idea of preload, which you can see very easily in your pressure volume loop. At this point, then, we move up to, if we move up now to point 2, once the pressure has built enough in the ventricles that we can push the aortic semilunar valve open, then we have our next phase, which is, give you a chance to answer that. Right, ventricular ejection. In my head, I see, all I see is everybody going, work, 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 work. Okay, anyway, I thought I'd try that. So we have ventricular ejection. Okay, we get to this point 3 then. At point 3, right, our volume decreases. Notice that our volume decreases. The pressure increases a little bit too, but that's primarily because we are we're squeezing hard on the ventricles at that time. Okay, once the pressure drops below the pressure in the aorta, then we are no longer able to push fluid out of the ventricle, and so we gave that a name. And right at that point, so then the pressure drops, and then we move down again to a pressure similar to what we had here. We don't have enough pressure to keep the aortic semilunar valve open, but we still have enough to keep the bicuspid valve closed. So we have another isovolumetric ventricular diastole. So that's what's happening between 3 and 4. Okay, now once this door closes, right, once this door closes, we had a name for that. What was that? What happens when the aortic semilunar valve closes? Yeah, we call that S2. So everything you need to see about the cardiac cycle can be contained here. Now we got one more point to label on here, and that's the point that happens here at the moment. At the moment where the pressure is great enough to actually push open the aortic semilunar valve, that has its own name too, and we call that the afterload. This is the pressure required to open the aortic semilunar valve, to open the aortic semilunar valve. Okay. So if we work our way all around this, then we have a very nice and compact and efficient way of representing what the cardiac cycle actually is. If you notice, we start here in late diastole, right? Our volume fills because we have a very low pressure in the ventricle at that point. And if the pressure in the ventricle is lower than the pressure in the left atrium, then our volume will increase. We get a little bit of a bump in volume and pressure here, but this is because of the atrial depolarization. We then get our ventricular systole, but because of the pressure, right, the pressure difference, we have isovolumetric ventricular systole, we have ventricular ejection, and then we have isovolumetric ventricular diastole. We can sort of put some ideas, some numbers in here for pressures. For example, this might be something like 120 millimeters of mercury. Make sure we use our units there. And this might be something properly like 80. Let's use some volume, which is going to be in milliliters. Let's say that this is 65. I think this is what the book uses, and 135. Now, for those of you who are thinking, we don't necessarily have a name for that pressure, and we do have a name for this though. What is that? What is this in terms of volume? What do we call that? I'm just going to use a similar color for this one. We call that ESV, right? This is the volume in the ventricle once it's contracted. All right. And then I think the final point that I would say here, at least a really cool thing about it, why I like it so much, hint, hint, wink, wink, nudge, nudge, is that if you look at the difference from here, right, that difference there in volume is stroke volume. Okay. So there you have it. That's called the pressure volume loop. It's just a third way of representing the cardiac cycle. And if you look at it, you have all of the different elements that you need. Late diastole, right? We have atrial depolarization. We have isovolumetric ventricular systole, ventricular ejection, isovolumetric ventricular diastole. So we have everything that you need there. Let's see here. I guess a fist to 5 at this point for those who are tracking. All right, so we're going to move on to the next board here. And quick pause. Okay, so what we're going to do now is we're going to actually transition into sort of modeling the fundamental equation for building up a model of the cardiovascular system, and we're going to use a fundamental equation that will help us do this. So to arrive this, though, we're going to recall our basic idea here that flow was proportional. Flow is proportional to a pressure gradient and inversely proportional to the radius. Now remember, we gave flow its own name. We called it cardiac output, and we said that that's proportional to a pressure gradient over resistance. So now what we're going to do, and we know that this is equal to cardiac output times, we know that cardiac output is equal to heart rate times stroke volume. What we're going to do now is we're going to rearrange this equation a little bit more to give us the following. I'm going to say that the pressure gradient is proportional to cardiac output times the resistance. Okay. What this equation tells us then is that a pressure gradient is generated whenever a flow encounters a resistance. And you can sort of think about then what the different combinations are, but we're going to give that pressure gradient now. We said that the heart is responsible for generating that pressure gradient. That pressure gradient produces a cardiac output that, as it then travels through your blood vessels, encounters a resistance. And depending on how much cardiac output or how much resistance you run into, your heart then has to generate a different kind of pressure gradient. We're going to call that pressure gradient now a new name. I'm going to call that mean arterial pressure, or MAP. And that's going to be the term that we use from here on out. And we can then define our equation, a new equation for the cardiovascular system that will say MAP is equal to cardiac output times, we're going to come up with a new name for resistance. We're going to call it total peripheral resistance. Okay, total peripheral resistance. And what this represents is the resistance of all of your blood vessels. In other words, when you can think of it as being, hold on, let me just try to write this out a little bit better for you. You can think of it as water moves through a hose, right? It encounters a resistance as it sort of rubs along the walls of the hose. Blood is no different. It is a fluid, and so it also then encounters a resistance as it runs into blood vessels. And so what we can then say, coming back to we're going to call this our guiding light, our fundamental equation for the cardiovascular system, and that is that mean arterial pressure is equal to cardiac output times total peripheral resistance. Okay, so we can think about, we normally play this game. We say, hey, if I increase my cardiac output, what happens to my mean arterial pressure? If I increase my total peripheral resistance, what happens to my mean arterial pressure? If I decrease cardiac output, what happens to mean arterial pressure? And if I decrease total peripheral resistance, what happens to mean arterial pressure? So you can think about this in all of these different ways, okay? And what we're going to do is we're going to say that MAP is equal to cardiac output, which we've just defined as heart rate times stroke volume, times, we're going to shorten this up a little bit. I'm going to shorten this up to just R. So R will just represent our total peripheral resistance, but that resistance is going to be a special one. And we're only going to focus not on the resistance of all of the blood vessels, we're going to focus on the resistance of the arterioles for reasons that we'll talk about in a minute. So let's rewrite this as mean arterial pressure is equal to cardiac output times the resistance of the arterioles. And we can say that the mean arterial pressure is the product of cardiac output and resistance. Okay, pause there. Okay, another pause. Okay, so what are we looking at here? We're asking the question, what do we mean when we say mean arterial pressure? In essence, we're going to sort of simplify and just think about it. What do we mean when we just say pressure, right? So just pressure in general. So what's depicted here is just sort of a cartoon schematic of your cardiovascular system. We know that oxygenated blood comes out of the left side of the heart, excuse me, so out of the left ventricle, and then it goes into your arterial blood, right? So the aorta and all your major arteries, and then it gets down to this part of it, right? So these would be arteries. And as you move down to smaller and smaller vessels, you get into these smaller vessels called arterioles. Okay, that blood then drains into your veins, right, where it then returns to the right atrium of the heart. Okay, and then these are your veins. So what we want to do is we want to sort of talk about when we talk about pressure, what do we mean when we say pressure? And so the way to think about that is that as we push blood into the arteries, then what happens is that they will expand. Right? They will expand because of the volume of blood that's been inserted to them. So that's why I'm kind of showing you here with these dashed lines. Okay, but then they respond to that by, sorry, wrong tool there. Right? They'll respond to that by snapping back and then pushing back on the fluid. So as blood pushes into the arteries, right, blood pushes on the walls of the arteries. And that is, in essence, what pressure is, right? The pressure is the force that the fluid exerts on the walls of these arteries. And as we'll see in the next board, your arteries have lots of muscle in them and elastic tissue, which means they can snap back. And therefore, what we can say is that your arteries act as a pressure reservoir. In other words, as the arteries fill with blood, they have elastic tissue and muscle that allows them to then snap back. And as they return back to their normal size, then that actually pushes on the blood and moves blood down the arteries, basically. And that's how you get that happening. We can then say then that as all of that blood then drains into the venous system, okay, it will also expand, right? So you could also say that we also would have a reasonable expectation as you push blood into the veins, right? They will also expand. But you will find that they have much less. They do not have as much smooth muscle. They have some elastic tissue, but not nearly as much muscle. So we say that the veins, right, the veins act as a volume reservoir. Okay, so they have less muscle, less elastic tissue. It doesn't mean that they don't have any, but they just have a less elastic tissue than your arteries do, which means that they can't, they don't then push nearly as hard on or they aren't able to snap back in the way that your arteries are. Okay, so we said that that's a volume reservoir. Now, if you remember back to some of the lectures that we've had in the past, that makes total sense, right? Remember, we said that if we have sympathetic innervation, right? If we had sympathetic innervation of the veins, then that would be enough to push blood back to the heart. So if we wanted to increase, right? If we wanted to increase our EDV, we could do that by simply having sympathetic innervation of the veins, and that would move more blood back to the heart. Okay, so along its entire length, there's resistance, right? As blood moves down the arteries, as it moves down the veins, all of those have resistance, and that contributes to this idea of total peripheral resistance. What we're going to be focused on, though, is just the resistance of these arterioles here, and that's what the green represents, because what we're going to find out here in a second is that the arterioles have a significant amount of sympathetic nervous system innervation. Oops, that's not going to work well. Start that up a little bit higher. Sympathetic nervous system innervation. So the arterioles receive right? And that innervation then leads to either contraction of the muscle that's in there. So these have a lot of smooth muscle in them. They're pretty much just all smooth muscle, as we'll see in a second. And therefore, they can either vasoconstrict or vasodilate. And it's the action of vasoconstriction and vasodilation, as we're going to say, of these arterioles, that leads to the bulk of what we're going to say is our total peripheral resistance. Okay? Pause for question. Move on. Okay. So we asked the other question, what do we mean when we say in the previous board, what does that mean when we ask, oh, I didn't pause. Oops. Okay. What we can do is we ask, what do we mean when we say pressure? But what we can also do then is track sort of how that pressure changes as a function of where it goes along the body. So when blood first comes out of the heart, obviously it goes to the aorta, and if you look at the aortic pressure and pretty much the pressure all the way through your arteries and down to your capillaries, it's going to oscillate. Hold on, here we go. Right, so that's going to change. Oh, that was bad. But you get the idea. Hold on. There we go. It's going to change. It's going to oscillate like this. And then as it moves along the body, we'll get to the capillaries, and then let's kind of carry this on home. Okay. In other words, what this says is that, as you leave the aorta, you have high pressure, and then as you move into smaller and smaller blood vessels, getting all the way to, for example, the capillaries, where we have gas exchange, you see that the pressure is pretty much falling all the way throughout. And when we talk about mean arterial pressure, we literally mean the mean arterial pressure. So if you were to take the average pressure here, smooth all that out, that's what you would see. So the black line represents mean arterial pressure. And you might think that you could just sort of add your diastolic and systolic and divide it by 2. It turns out that's not the case. Hold on, a little bit of, get rid of that there. Mean arterial pressure. But it turns out it's not just simply an average, it's like a weighted average. I'll leave it to you to check that out in your lab manual to see how that's actually calculated. Okay, but what this says is that as you move through your arteries and you get down to the arterioles and smaller blood vessels, okay, you'll see that pressure starts to drop. And then once you get into the veins, let me fill this in here. So we got veins. And then before you get to the capillaries, you have the arterioles. Okay, but you can see that as that happens, your mean arterial pressure drops. This is sort of like not really that surprising, right? As you encounter, as you move further and further along a blood vessel, then you're sort of having to do more work to sort of keep blood moving along. So that's actually not surprising. So the big idea is that you need this then. So when we talk about what we mean by mean arterial pressure, if you want to maintain this sort of high pressure that you see here, then that tells us then that you need to have something functional about the arteries and the arteries. So hold on, fill one more. Arteries. All right, so it tells us that we need to have something special about the tissue that makes up your aorta, your arteries, and your arterioles that allows them to have, sorry about that, folks. Oops. That allows them then to maintain this relatively high pressure. And that's what we're going to look at next. Okay, so here what I'm asking, this is I think figure 15.2 and 15.2 in your textbook, I think. So why arterioles? And what I mean here is like, why are we using them as our measure of resistance rather than all of the blood vessels taken together? What I want to bring your attention to, that's sort of like we said, let's think bigger picture first. We had arteries and veins. We said that arteries were what we called a pressure reservoir. So why is that? Well, we noticed that, as we said, they have some elastic tissue and some muscle. So if you look at the amount of elastic tissue that's present in your arteries, what this means is that as they fill with blood, that elastic tissue then allows them to snap back, so to speak. And as they snap back, that pushes against the fluid in the artery and moves it further down the blood vessel. If we look at our veins, we look at our veins. There's hold on, give me a bit. If we look at our veins, they have much less of that elastic tissue. They have some, but they don't necessarily have enough to sort of allow them to push back on the vessel. And you can get a sense of that by looking at sort of just this cross-sectional area here. It's all color-coded, so you can see there's much less elastic tissue there than there is when you look at your arteries. So that's why because of this, that makes it a good pressure, that makes your arteries a good pressure reservoir. But it also, the presence of elastic tissue makes your veins a good volume reservoir. Now, just as a sort of like a clinical aside, we know that as you age, then what you will find is that you can you'll find that you'll lose the elastic tissue in your veins, and that's what it gives rise to what we call varicose veins. So you just have that as a clinical application. So the other thing that we can think about is then arteries. So why are we looking at the arterioles? As you can see, they basically don't have anything but muscle. And so if you look at the shape of the arterioles, you can see it's got a ring. It's basically one cell layer thick. These are endothelial cells. Shout out to Dr. Altman. She loves her endothelial cells. These are the things that that gets her all super excited about going to the lab and working in her lab. So there's shout out to Dr. Altman in case she didn't think she was going to get noticed. Then we can say that they're essentially just their muscles. So if we look at the contraction, right, if that smooth muscle contracts, what's going to happen to the radius of that blood vessel? It's going to get smaller. And if that muscle relaxes, then what's going to happen? Then the diameter that's going to get larger. Okay, so basically, then it's going to be the diameter or the diameter of these vessels that will determine your resistance. Because if we think about it, right, these are the things that are coming to your these are the things that are coming into your capillaries, right? And so if we decrease the radius, for example, then we'd have less blood coming into the capillaries. But what would happen to the pressure behind it, of the fluid behind it? Right, so we'd actually see an increase in pressure. If we increase the radius, though, we made it wider, then what's going to happen to the pressure in the blood coming behind it? That actually will go down. So guess what? You can see that there's this inverse relationship between radius of the blood vessel and pressure. And this will be absolutely fundamental to what we're talking about as we continue talking about mean arterial pressure. Pause. Okay, so as we just talked about, right, we said that really the business end of our mean arterial pressure, for our intents and purposes, again, I want to be clear, it's not that the other blood vessels aren't offering anything in terms of how they're contributing to resistance, but the fact is that our business end is going to be changes in radius. So we can actually define an equation, as we're showing you here. We're going to say that the resistance of a blood vessel is going to be equal to just the ratio 8 over pi. This is just a constant, so I wouldn't necessarily worry about having to calculate that out, times L. And L for us means the length of the blood vessel. The length of the blood vessel. There we go. In other words, if you make your blood vessel longer, then there's more blood vessel for the fluid to interact with, and therefore your resistance will increase. This is not an N. It actually stands for the Greek letter eta, and it stands for viscosity. Now, viscosity is just sort of like the thickness of the fluid. So if you think about motor oil, it doesn't flow nearly as well as water does. Okay, those terms are in the numerator, right? So if we increase the viscosity, right, we make it harder for blood to move, then we've increased the resistance to flow. In the denominator, though, we have this term here, which is R. That's your radius. And notice that it's not just the radius, right? It is literally that's the radius raised to the power of 4. So it's the radius of the blood vessel. And because it's in the denominator, it has a very profound effect on resistance. Because if I increase my resistance by sorry, if I want to increase my resistance, then what do I need to do to my radius? Well, I need to make it smaller, right? Because if I make this really small, then this product becomes really big. If I want to decrease the resistance, then I just make my radius bigger, because if I make the radius bigger, then that makes this term smaller. So what are we going to be focused on for this idea of resistance? Basically, what this says is that if you want to change length, you need to become either taller or shorter. Or, in some cases, people have amputations sometimes would see something that looks like this. We'll assume that won't change. No one's going to have a severe accident while they're in class. Viscosity, on the other hand, we shouldn't really expect that to change either. Unless you basically just totally dehydrate yourself so that you remove all of your plasma, that wouldn't change. An interesting thing, though, that you will see with this is one of the reasons, at least as far as I understand it, that cyclists are caught blood doping. Essentially, what they're doing is they're trying to pack their cardiovascular system with red blood cells, overloaded with red blood cells. So you can imagine if I've got just 4 times as many red blood cells, they're not going to fit through those blood vessels in the same way. So that would be one way of increasing viscosity, but it's not something we're going to really focus on. What we can do, again, because of that sympathetic innervation of our arterioles, is we're going to focus on the radius of our blood vessels. Okay, and so how can we change the radius? Well, as we said in the last board, that means we need to change the diameter or the radius of the blood vessel. Okay, and to do that, we have to learn our last bit of muscle for the semester, and that is smooth muscle. Okay, so I'm just going to sort of walk through sort of what it looks like. Okay, when we talk about smooth muscle, and what you can see here is what I'm doing is just two muscle cells, 2 smooth muscle cells. They have the same basic proteins that you find in the other types, as we'll see here in a second. But now we have to sort of get used to it. Notice that they're not sort of arranged into these sort of fine sarcomeres or anything like that. They seem to be just kind of sort of like haphazardly arranged, and that's actually by design. So what you will find is that you will have these structures called dense bodies, which are which are the dark blue here. So those are dense bodies. They act as anchorage or attachment points for your thin filaments. Sorry about that. So those have the same sort of representation. So in red, at least I'm sorry, in this red, those are your actin filaments. So you still have actin, and as well, you also then have your myosin. Okay. Now, what you'll notice is that because they're not organized, they don't have this orderly arrangement of sarcomeres, then they won't necessarily pull in one direction. Not the boy band. Yay! They don't always pull in the same direction, and that's actually kind of by design. What that then allows, it allows you to generate lots of different it allows you to attenuate force in lots of different, because you can exert force in different directions. In other words, what that means is, if you have, part of you have some actin and myosins that are pulling in this direction, for example, and then you might have down here, you might have them pulling in that direction. Well, they're not exactly pulling, in the same direction. So that actually allows you to generate different kinds of force. And then the green are so the different muscle fibers are actually connected by connective tissue. Okay, so this is smooth muscle, and that is what we said. This is the primary component after those endothelial cells of your arterioles. If these muscles contract, they will change your radius. If they change your radius, then they will change. If these muscles contract, they will change your radius. If they change your radius, then they will change your resistance. Okay, and that's the game we kind of play with that. And again, the key thing too is to note that you're not just raising it to by 2, if you doubled, right, if you made R go from 1 to 2, it's actually going from 1 to 16, which is that's a pretty big change there. Okay, so we've talked about different kinds of muscle up until this point, so let's make sure that we kind of look at them in a sort of like a collective way, just to kind of make sure if we start talking about them on an exam. So first of all, we noticed that the appearance of our skeletal and cardiac muscle, they were striated muscle for both. But there's no sort of arrangement, appearance in terms of there's no appearance in terms of how the fibers are arranged. Excuse me. Let's see. They are arranged, so they have an orderly arrangement because of that. And then not orderly. So at this point, you might be thinking, okay, well, kind of what's the point of them if you have essentially they're not looking like anybody else, right? So they're right, some sarcomeres, right? Just to make sure we're and then if we but there are some similarities actually. So if we just move, I'm going to move proteins down a little bit, just to give myself some space. Well, we already know that our skeletal muscles had what they had: actin, myosin, troponin, and tropomyosin. Your smooth muscle has all of those except troponin. All but, that'd be a different way, a better way of saying it. All but troponin. Okay, so you have the basic elements, and I think I was saying this too when we looked at like skeletal and cardiac muscle. There aren't very many isoforms of like actin and myosin that exist, and I think that's sort of just a testament to the fact that once you kind of figure out what you need, you don't really deviate from that too much. Okay, let's see here. All right, so therefore, right, changes or contractions, contraction, relaxation of smooth muscle change the radius of an arteriole, and therefore, that's what the dots represent, change R. But again, make sure that we sort of are thinking about this the right way. If I excuse me, if I increase the radius, I decrease the resistance, right? Because I make the radius bigger, which allows more blood to flow through more easily. And if I decrease the radius, then I increase the resistance, right? Because there's less blood flowing through, and as the blood builds up behind it, it exerts more pressure on the walls of your blood vessels, and that causes you then to have to change or increase your pressure. So that brings forth the obvious question. Pause for writing. Okay, so we've got to think about then, essentially, if we want to change resistance, we've got to figure out how to do what? Make our smooth muscle contract. So what we're looking at here is smooth muscle, right? ECF, ICF, all of our regular players that are here, right? We're going to start with contraction on the left side, and then relaxation on the right-hand side. Okay, so note the arrow there. It's just sort of going through a temporal perspective. Now, remember, what was the one thing we needed if we were going to have muscle contraction? We needed two things. We needed to have we need calcium and ATP. And the only question, if we're depending on what type of muscle we're talking about, is where's the calcium coming from? How's it being used? Right? Where is ATP coming from and how is it being used? Okay. So when we look at smooth muscle, it's just like any other muscle. So we're going to have some calcium. And here's where things get a little bit wonky. So we're going to have calcium entry. Right? So if we had like a step 1, we're going to get calcium entry. And that could just be from any known cause, from external or internal sources. We'll just have calcium entry from the ECF. There are lots of reasons why you could have that, but strain, for example, might open calcium activated stretch receptors. We just want to say we have calcium entry from the ECF. Excuse me. Once we have that, then we're going to combine that calcium. That calcium is going to help us out. We're going to get a little bit of calcium-induced calcium release. So let me put a little bit of we get a little bit of calcium also coming in. Get some calcium as well. All right, so I'm sorry. So to rephrase then. So we could either have calcium entry. Apologize. Collective grown on 3. Right. There we go. So we have sort of like a calcium entry or a calcium signal. That's what I should say. Right. Calcium entry. So we have calcium entry generates a calcium signal. Again, that could be coming from an external entry, or it could be coming from internal stores through sarcoplasmic reticulum. Okay, as we continue through, then now we get something interesting happens, and that is we get a new player in the game here. And what's unique about calcium, just in general, is that it's able to when we talk about cell signaling. Calcium is unique in the sense that calcium can be like its own second messenger. It doesn't necessarily need to act through a bunch of intermediaries in terms of a signaling cascade. It can literally, if it wanted to, it can literally activate things on its own. And that's kind of what we see here. So we're gonna bring a new player in called calmodulin. Okay, and that forms a complex that we'll call calcium calmodulin. Okay, so that's going to be step 2. Get a calcium calmodulin complex. And then something interesting happens. What that complex is going to do is it's going to combine, it's going to work through whatever process it does to using ATP, so calcium and calmodulin together, will work with ATP to take this protein called myosin light chain kinase. So to see the note down here, myosin light chain kinase. It's in its inactive form. But when you have calcium combined with ATP, it can take that inactive MLCK and convert it into active MLCK. And let me just write that a little bit differently. Active MLCK. Now this is a kinase, and so a kinase does what? That's right, it phosphorylates things. So its ideal then is that it's going to add a phosphate group to those to the myosin heads. So let's make sure the step back, kind of write out our points. Right, so we're going to say step 3. Oops. Oh, that wasn't good. So step 3, right, that will activate MLCK. And let's make sure we say calcium calmodulin activates MLCK. That will then, the active MLCK then in step 4 will phosphorylate, that's phosphate, phosphorylate the myosin. That will lead to step 5, contraction. Okay, so it's a quick review. We get calcium entry. Calcium entry could be either from an external source or an internal source. Calcium then combines with calmodulin, okay, to form this calcium calmodulin complex. Together, they combine ATP and an inactive MLCK to make it active MLCK. And then the active MLCK then will phosphorylate myosin, which leads to contraction. Right, process is, again, there's a process here, so make sure that you're thinking about it. But I think there's a good way of looking at it from the perspective of, okay, this one is a little bit wonky relative to what you've seen from cardiac and skeletal muscle, but they still involve the same things. Just what are we doing with it? Okay, and just to make sure, for clarity's sake, this is just a phosphate group. That's what that represents. Oh, let me write it in. That's a phosphate group. All right, so there's our contraction. Now what we need is for contract, we have to relax. Okay, so a few other notes here. So this is myosin. Writing it here. Now if we just sort of take a look at, if we think of everything that we've done with cardiac and with skeletal muscle, we brought calcium in, and then what we needed to do, we needed to put calcium back, because that would be the thing that would keep us from, or at least help us with relaxation. We don't necessarily have calcium acting directly in the contraction here, though, right? This is, there's no calcium here per se, right? So what do we need to do then? Well, if the phosphorylation is what leads to the contraction, we need to take that phosphate group off, okay? So now if we look at that and kind of carry it over, and let's make sure we'll take that phosphate group off. Right, so we say step 6, the myosin light chain phosphatase, a kinase puts phosphate groups on things, a phosphatase cuts phosphates off of things. So let's look at that. I'm going to say step 6, MLCP removes phosphate from MLCK. At that point, if we remove the phosphate group, then MLCK, right, it inactivates or makes your MLCK inactive, and therefore it's no longer phosphorylating. It's no longer phosphorylating your myosin. Okay, so then what do we need to do? Well, now we've got to put the calcium back. So now we just sort of run our process back. Okay, we're going to take off our wrong color. Take off our calmodulin. And then what do? Well, we have to put our calcium back, right? So we put our calcium back in the normal way to our calcium ATPase. Right? And then we do the same thing, right? Now we have another calcium ATPase. So same thing as before. So that's a calcium ATPase. And we have our good friend, the sodium-calcium exchanger to also help us with that. Right, so we take out calcium and we bring back in sodium. So this is our good friend, our NCX. This is just our calcium ATPase. All right, so let's fill that in. 7, calmodulin separates. So, sorry, wrong way. Put that over here a little bit more. Calcium calmodulin separate. And then 8, let's not put it there. 8, resequester calcium. And we have our normal ways. We can either put it, back into the SR if that's where we need to. We can put it to the ECF via our sodium calcium exchanger, or if we need to, we can use a calcium ATPase. I think the main thing is that this just says, hey, it's an all hands on deck situation. Let's get calcium out. Now let's go back to what we were looking at over here. Remember, we said that calcium may not be actively involved the way it was for skeletal muscle and for cardiac muscle, but you still find that if I've got calcium around and a calcium calmodulin is available, then that should lead to contraction. So let's just make sure that we fill this in. So this part is relaxation. All right, process. Now I want to sort of kind of summarize what we've just done here by sort of giving you a sort of a way of thinking about it, because essentially what we're going to have to do moving forward is that we've got to understand changes in radius, because that change in radius is going to be the thing that will be our primary determinant of changing our total peripheral resistance, and therefore changing our mean arterial pressure. Okay, so what I'd like for you to, the way I try to think about it is I've got sort of this amount, these two molecules fighting against each other. If I have MLCK, right, MLCK will promote contraction. If I have MLCP, that will promote relaxation. So if we just sort of took the ratio of these in very, very broad strokes, this is not how it's done, but just in very, very broad strokes, what we can say is that if this ratio is greater than 1, then that will weigh towards contraction. In other words, right, the only way for this relationship to be greater than 1 would be for MLCK to be greater than MLCP. Right? So if MLCK is greater than MLCP, then that should lead to that. On the other hand, we can also say that, well, what if we go the other way? If we go the other way and that this relationship is less than 1, right, then that should lead to relaxation. Because in this case, what we're saying is MLCP is greater than MLCK. And if that's the case, then what'll happen to our radius? Well, here we'll decrease our radius, which does what? Increase our resistance. Here, if we do this, this will increase our radius because we'll relax, right? That's called, and then that will cause our resistance to decrease. Now we have names for these. We will call contraction vasoconstriction. So if we vasoconstrict, right, and then we'll call relaxation vasodilation. Okay, in other words, if we vasoconstrict, that means we're decreasing our radius, and that will increase our resistance. If we vasodilate, we increase our radius, make them wider, make them larger, but that decreases our resistance. Okay. All right, so I'm going to stop it there. This is our first time. Hopefully, we made it through. Everybody survived it, including myself. Some elements about this that I think I like. Some elements that I'm going to try to improve. Basically, what you saw, I kind of noticed that I had a laser pointer function, so that was kind of helpful for me to be able to think things through. So. Yeah, so hopefully some of you were able to get what you needed. Again, come to office hours and let me know how it went. So thank you all for your time. Keep rowing that boat, yeah? Can't really stop. We always have to row the boat. I'll talk to you soon.